All right, good morning. So we will start today on the content for Signature systems. All right, so let's look at some properties. So this is the most basic theoretical component of the course. We'll start from the simple stuff and move along to more complicated things as the course progresses. So this topic basically leads up to what's known as linear time invariant systems. Okay. So we'll start with the concept of linearity, right? And then we'll look at basic components like amplifiers and mixers in terms of how linearity affects their performance. Then we'll look at time delays and look at the properties of time invariance, and we'll go from there. So let's say we have some signal function of time. Signal is x of t, right? So x of t means x is a function of time. It varies as a function of time. So x could be a voltage, it could be an electric field, a magnetic field, a current, a charge, some physical quantity that varies as a function of time. So for ease of use, let's say it's a voltage. Okay, so we'll call it a voltage. Voltage at a terminal. So it varies, right? So it's a waveform. So these things are called a waveform. So if I have a system of some sort, this could be some sort of circuit. We really don't know what it is at this point, but we apply as the input. So this is the input port, x of t. So if I measure what's going on at the input, I can see, let's say if I have some instrument that allows me to measure the voltage as a function of time and display it on a screen, I will see a waveform of this shape going in. So let's say I apply this waveform here, and then I call the output waveform y of t. So I provide some input and it produces an output. And if the output is simply a scaled version of the input, no change in the shape except it's just got bigger, then we can say that, okay, we'll have this is a scaled version. So here's my output. So this of t is y. So if I can relate x of t to y of t using a constant, some a times x of t, where this is a constant. All that this a constant is doing is it's just bumping up the value of x of t by some fraction, right? So this constant is known as the amplification. We call it also the gain. Okay. And the circuit that achieves the scaling by a constant a is called an amplifier, right? So we have a special symbol for this. It's a triangle.
Is that an op amp?
No, it's just an amplifier. So op amp is just a type of amplifier. Okay. So operational amplifiers or op amps are a type of amplifier that you can use to get the functionality, but this is just a generic amplifier. Okay. So the amplifier in ideal case has some properties, right? So we can say, okay, the amplifier, an ideal amplifier, so properties of frequency independent gain. So we'll come to that soon. But for now, just take my word for it. So this gain A does not depend on any other variable like frequencies or time or anything. It's a constant. A is a constant. A is a constant. And A is greater than or equal to 1. Linear behavior. So by linear behavior, what it means is if you relate the input and the output, right? But plot input X against Y. When the input is 0, the output has to be 0. Very important. So we'll have a line like this. This is a straight line. Straight line relationship between input and output. It's in the Y is equal to mx form. And we have this angle theta, where tan theta is equal to the gain. So two important properties. It takes the Y equals mx form, not Y is equal to mx plus c form. Okay. Linearity, by definition, requires that your output is 0 when the input is 0.
So the wavelength it has a linear behavior.
Has what?
It has a linear behavior.
Which one?
The wavelength, because you said tan of theta is the amplifier. So I'm asking, is the amplifier linear?
I'm not following your question. What do you mean?
Because what you draw up there is like a sine function, right?
Oh, it's an arbitrary waveform.
But this one is linear.
So good question. So this is the variation of X or Y as a function of time, right? This is Y plotted against X. This is not time, right? So for every value of X, Y is simply a scaled version of it. It's linearly scaled. So it just makes it bigger, right? So X of t itself could be any waveform. But for any value of X, Y is simply X scaled by A. All right. Yeah.
Okay, so if I understand your graph, X and YT are different like voltages, right?
Different X and Y are different what? Sorry.
So can you please explain the graph to me again?
So this is X and Y as a function of time.
Mhm.
How it varies as a function of time. This one is Y as a function of X. So for any given value of X, what is the value of Y? Right? So it's a relationship between X and Y directly. Nothing to do with time. This one has time as the independent variable. This has X as the independent variable. Yes.
So on the linear time, it's so the input, let's say, is 1. Is the output always going to be 1, or could it vary?
It's going to be A. For input 1, output is going to be A. Right?
Okay.
Because everything that's scaled, any value of X is scaled by A at the output. So if your input is 1, output is going to be A. Right? Plug in. So you can see that by taking this relationship, right? Right? Y of t is equal to A times X of t. So input is 1. This is basically a constant. That's 1 as a function of time. Right? So you will get 1 times 1. Right?
Yeah. The x of t, that's where the 1 is, but I'm guessing the x of t is the vertical.
Yeah.
Okay.
Right. So this is X of t.
Okay.
So because you chose X to be just 1, it's not varying. So when it's not varying, the output is also not varying, even though as time goes by, it can vary. And it's simply the input is 1 times A, which is equal to A. So I can ask a problem. Let's say y of t, want to make sure this is covered, okay, y of t is equal to a times x of t. If x of t is equal to, let's say, b cos omega t, find y of t. So plugging in, we can get y of t is equal to a times b times cos omega t is equal to ab. So interestingly, the recording has everything mirrored. Does anybody know how to fix that?
Is it on Zoom?
On Zoom, yeah. There should be a way to mirror it, just to mirror everything, right?
Right here, it shouldn't be muted. Oh, you want to mute it?
No, 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 it's not muted. See, the board
Mhm.
is mirrored.
Oh, it's flipped, maybe,
Oh.
but maybe if you watch it, it's not flipped.
I wouldn't count on it. Are you sure? I'm pretty sure they're not gonna.
I can join the Zoom and then I can see.
Yeah, I think. Let's check. All these, they're in the settings though.
Hmm?
Well, we live in the settings.
Can you?
100%. There's actually people in this meeting.
Video settings, mirror my
No, there's nobody.
It says mirror
It's
my
just for
video.
recording.
It's like,
Mirror, yeah, do that.
there you go. So now it's
Yeah.
regular.
Thank you. Thank God I noticed it. Otherwise, the whole screen would have been completely useless. So that's good. Oh, it's correct now.
Okay, two questions. One, I don't understand the writing right here on the second graph. It says y equals something. I don't know what that means.
Where? This one? This? This part?
Yeah, I want to clarify what it is.
Oh, no, so y is equal to mx is just the standard linear, graph form, right? So you have a x and a y.
Oh,
And
okay.
yeah, so m is equal to the tangent of the y.
So it never have a wire intercept. It would never have an intercept. Like it would never be from the origin. It's because mx, there's no plus a number on the y intercept, so it's always going to be on the origin.
So you're talking about plus c part,
Yeah.
right? So you can, you have amplifiers which have it, but according to the definition of linearity, that's not a linear amplifier, right? So in order for the linear amplification to occur, you can't have an intercept because when the input is zero, output by definition is zero. So the moment you have a linear part, just like some DC, you can convert that amplifier into a linear version by some techniques. But we are trying to keep it simple and okay, this is a linear amplifier, this is just the mathematics. Okay. So let me erase this now.
So you can technically find the slope of a linear line with tangent theta.
Yeah.
Never knew that.
It's the slope is the tangent. Right? That is the tangent by definition. So you can see that by looking at, right, say, if this part is, let's say, alpha and this is beta and this is theta, tan theta is by definition alpha over beta. Right, that's by definition.
Yeah.
Because we said so.
Okay, one more thing. I see like a straight line in the middle of YT in that graph. What does that mean?
Oh, so I just showed how this scales to that value.
Oh, okay.
Right, it's just grown bigger by that amount. Let's draw something else. Okay. So let's do a problem. Let's say a linear amplifier has gain of A equals 15. So an input x equals 3 sine 2 pi n t minus 1/4 cos 2 pi 11 t. Find the output signal y of t. So I define the waveform. It's got two components, two sine waves with two different scaling values. Just a function, right? And that function has some shape. You apply this thing into an amplifier and it produces an output. So my amplifier has a gain of A is equal to 15. Input is x of t, output is y of t. So we know that y of t is by definition the gain times x of t. So I can plug in values. A is what? 15. And the waveform x of t is this one. 3 sine 2 pi times 10t minus 1/4 cos 2 pi t. Okay. So I can simplify. 3 times 15 is 45 sine 2 pi t minus 15 over 4. Any questions?
For an original expression that's out of the cosine is pi of 11.
So the cosine waves take the form cos omega t, where omega is equal to 2 pi times f, right? So in this case, f is equal to 10. In this case, f is equal to 11. These are the two frequencies. We convert that into circular frequency and then write the function. So let's do a second problem. The input to an amplifier with gain 3 is shown. So I'm giving the problem in a graphical way. Or I'm saying, okay, the amplifier gain is 3, right? So we have an amplifier which has a gain of 3. This is input. This is the output. And I'm defining the input. So these are time values. Time t1, t2, t0. This is alpha. This is my input x of t. So this is my waveform going in. I'm asking you to plot or sketch the waveform that's coming out. So the only thing that the amplifier is going to do is going to scale the input by a, right? So if you know the input is x, the output is a times x. So in this case, we know gain is 3, right? So this whole waveform is going to be scaled by 3. So I can write or I can draw the output against time. So this is my y of t. I still have my time values t1, t2, 3, 4. So originally it started from 0 and went up to alpha. But now that whole section is scaled by the gain 3, right? So instead of alpha, it's going to go up to 3 alpha. So we will see something that's doing that. Come back to 0. That. Three. Okay. So this point is going to be 3 times alpha. This height is going to be 3 times alpha. It simply scales the output by gain, right? Nothing else. It doesn't change the shape by any means except scaling it up or down. So if alpha is less than 1, it's going to shrink it, it's going to make it smaller. If alpha is, sorry, if A is greater than 1, it's going to make it larger. If A is less than 1, it's going to make it smaller. For A less than 1, amplifier is called by a new name, attenuator. So attenuators make the signal smaller, right? You can think of it as a special case of amplification where you don't actually make it bigger, you make it smaller than the input. So typically amplifiers which are less than 1 gain can be realized without any power source. It's a lossy circuit. So you can basically make the signal smaller very easily. It's basically called an attenuator. But even though the circuit types for amplification and attenuation are completely different, mathematically they appear the same. It's just scaling the input. Okay, so we talked about linear amplification. So let's look at a different type of system, which is not an amplifier, right? But it's super crucial that you understand what this new one is. We call it a delay, time delay. So imagine you have a system. This is a delay. See, so the input is xt, output is yt. So what happens here is that you don't change the shape of the waveform in amplitude domain, but you simply shift it by some value, some delay tau. It comes out tau seconds later. Let's put it that way, right? So if you have a box which has a wire and you send in a signal, it waits for certain amount of time, which is the delay, and the signal comes out unmodified. No change except that it got held back, it got delayed inside this box. So this is called a delay line. And we can think of it as, okay, y of t is simply the input x of t, but it's got a delay, which means that your time variable or time axis has been shifted by some constant value tau. So you can write that mathematically by having a negative sign by convention t minus tau. So this is my constant delay. This is my variable. So t is a variable, so this is real valued. And tau is also real valued. So here this funny symbol, this R with two strokes, is a mathematical symbol for real numbers. So note R notation for the set of real numbers, i.e. the real line. So we can visualize this in a graph, okay? So let's say we have a waveform time and x of t. So for simplicity, I'm going to start with time equals 0. Let's say my waveform does this. This is my input. So let's say this is t1, is t2. This is time 0. So when I apply this steppy waveform into this box, the delay line, it spits out the same waveform tau seconds later, but no changes. No change in amplitude. It doesn't get messed up in any way. It comes out as a pristine copy, but just tau seconds later, it's got delayed. So you can write that or draw it on the graph. Okay, let's decide tau to be somewhere here. So this is my tau. So the whole thing is shifted in the time axis by tau. So it goes as 0, jumps here. So this difference is tau. Right? You can see it here also. So you can see the same shape, just moved by tau. And that moving in time is simply, it's waiting a little bit of time, tau, before it sends tau, right? So the simplest possible way of achieving a delay is through a cable, right? Because we know that the signal propagates through the cable at some speed. So if you know the length of the cable and if you know the length of the cable and the speed at which the signal propagates, you divide the length by the speed to give you time. That's a time delay, right? Let's say it takes 10 meters per second and it's 10 meters long. The thing is going to come out 1 second late, something like that. So we can draw it. I'm going to erase this because just to get a clearer view. So imagine you have a cable. So I'm going to draw the cable like so with some length. Okay. So let's say this is a long cable that is L meters. This is my cable. So let's say the speed of the signal, speed is, let's say, V. So V is something that is less than the speed of light. It's almost the speed of light, but not quite. It's about 10% slower than the speed of light in vacuum. Very fast, right? So these are very, very fast signals. So you put x of t here, and you get y of t out. It's going in, coming out, and it takes tau delay. So we can find tau is simply distance divided by speed. Speed of propagation of the signal, which is simply L over example. Okay. P is equal to 0.9 times 3 into 10 to the 8 meters per second. So 3 into 10 to the 8 is speed of light. So C is equal to 3 times 10 to the 8 meters per second. And this is a scaling constant. We call it the velocity factor of the cable. Okay. L is equal to, let's say, 3 meters. So find tau. So tau is equal to 3 meters divided by Can somebody work it out? How much? Sorry, what? Did you say something?
No.
No, okay. So 1 over 9. So our answer is going to be 1 over 0.9 into 10 to the minus 8 seconds. How much is it?
1.1 times 10 to the negative 8.
1.1 times 10 to the negative 8, right? So that is basically 11 times 10 to the minus 9. So 10 to the minus 9 is nanoseconds, 11 nanoseconds. So it takes 11 nanoseconds for the signal to propagate from input to output, given that the velocity factor of the cable is 0.9 and your length of the cable is 3 meters. So if you know the velocity factor of a cable, you can find the time delay the cable imparts on the signal. And the interesting thing is that it does not depend on what the signal is. It's signal independent. All signals propagate at the same time delay, right? It's only a property of the length of the cable, that's all. And the velocity factor. Take pictures also.
Is it, so the velocity factor of the cable, is it always gonna be times by the speed of light?
It's always less than, so the velocity factor is the coefficient that you scale the speed of light by to get the actual speed.
So every, like, let's say you have, another example, 0.75 or 1, is it always gonna be times the speed of light?
Yes, and it's always going to be less than 1.
Okay,
So the fastest you can possibly go is the speed of light. And the only way to get that is through free space by wireless. Every time you have a cable, it is always slower than the speed of light. Always, always. Never the same. It's always slow. So that's why optical fibers are slower than wireless. So they use that for, they use that fact for automated trading. So most of the networks are fiber and they're slightly slower than wireless. So the guy who has a wireless link can actually put the signal back at the receiver before the optical network catches up, and they make money from that. Huh?
the optical is what?
Optical is about 10% slower than wireless.
So optical is like
Optical fibers.
wireless, and then the wires obviously it goes faster.
Yeah, so even if the cable is an optical fiber, it doesn't have to be copper, it's any form of cable. It's always slower than wireless.
Always slower than wireless. Oh, so wireless is always faster than,
Wireless is always faster.
and that's because it's the speed of light.
Yeah.
Thanks, sir.
So typically I take a picture and share in the group, but I forgot this time, so I'm not starting.
I can send it to you.
Okay, thanks. Okay. So now let's try to combine the two properties that we talked about into one property, right? So the two properties, linearity and so linearity means y of t is equal to a times x of t. Time invariance means y of t is equal to a t minus t. To have an input x, if the system is linear, the output is always a scaled version of the input. That's linearity. So if the system is linear, the output is always a scaled version of the input. The system is time invariant. That means any delay that you impart on the input side will cause a corresponding delay on the output side. So I can take x and delay it by, let's say, t, and that same time delay is just imparted on the output of the system. So my output is going to be now x t minus tau. So I can think of this as a new time variable t prime. So I can write this as x. So to give you an example, let's say we have a system that is linear and time invariant. If x of t is equal to 3 times cos 2 pi 10t and find y of t when t minus tau is equal to 5. So I'm taking the same system, okay, and I'm connecting a delay at the input side. So I can take the same system, I'm connecting a delay line and the same system. Okay. So my input is applied here 3 cos 2 pi 10t. And I'm asking what is the output in terms of y. So the only thing that happened is we don't know what the gain is, we don't know what the internal delay is, we don't know anything. The only thing that we know is that it's linear and time invariant. So that means if you apply a signal, it's just linearly scaling in amplitude domain. If you delay the input, the output is also similarly delayed. So the only thing that we have done here is that regardless of what x and y are, we delayed the input by tau. So I am going to now have the model here, the input model is cos 2 pi 10 a minus tau, right? So the only thing that happened is I delayed the time variable, the time nature of it by tau, right? And irrespective of whether what shape x and y are, right? Some shape of x is producing some shape in y. But the only thing we are doing is we are delaying it by tau. So it's just going to come out delayed, no change. So we don't know what exactly y is, but you can just write y in terms of the previous one as y t minus tau is equal to y. So it's a little tricky. The point I want to make here is that if we know that the system is linear and time invariant, we don't have to know what x and y actually are. But we can do some change to x and find out what the corresponding change to y is in terms of the variable y. Okay, so we delayed x by 5, so y also has to be delayed by 5. That's all. Very simple.
So is that the answer?
Yeah.
No. So this is just a quick summary. The first part of the wire, the 3 cosine 2 pi 10 time,
Mhm.
that's the input before the wire,
Exactly.
when the wire.
Exactly. And I referred the input to time that's happening here.
Yeah.
Right. So this is the function as a function of the time reference to this signal.
And the wire part.
Yeah.
The wire delay is the part where you change the t into t minus tau.
Yeah.
Okay.
Exactly.
So where's the delay again?
So that's a wire, right? So this wire is, let's say, some L long.
Yeah.
So because of it, when you put the signal in at this end, it comes out a little bit of time later, right? And if the length of the cable is L divided by the speed of the signal is that delay, right? So what we are saying is that if you directly connect it, it produces an output. If I just connect a delayed version, it's only going to delay the output. It's not going to mess it up. Essentially, that's what it's saying, right? But there are some systems where you can't do that. It produces something when you connect it to over here, but if you wait a little bit, it's gone all messed up and it produces some complete garbage. So that is not a time invariant system. We are saying our system is well behaved. We can delay the signal and we are guaranteed to get a delayed copy of the signal without any other things going on. Very simple concept, right? So you can plug the system in tomorrow and you're guaranteed to work. It's going to work exactly as it works today.
How in this case is the propagation of the signal?
Yeah. Propagation delay. So let's do one more bit of math and then we'll close for today. So we call this the linearity property of LTI systems. So let's say we have a system that's linear. If I give xt, it produces 1 by definition. So what that means is I can take any example of input. Let's call it x1, right? If I give it x1, it's going to produce the corresponding y1, right? So x1t produces y1 of t. A different example, x2t will produce its corresponding y2t. So if we know that x1 produces y1 and x2 produces y2, we can scale x1 and x2 by different amounts, add them together and make a new signal, and the same scaling operation happens at the output side. So let's say I take a new one, x3 is simply alpha times x1t times beta times x2t. So what did I do? I took x1 waveform, scale, put an amplification factor of alpha, scaled it, right? I took x2 separately, scaled that by beta. The resultant values I added together to make a new one called x3. So we want to find out, okay, what is the output for that compound signal? So you can find the output of the compound signal in terms of the individual components that the individual components are of the input side are going to have. So we know x1 produces y1. So alpha times x1 produces alpha times y1, right? And beta times x2 produces beta times y2. Okay. And they're additive. So you have the two components. Because we added them over here, we can add them over.
So is the YT, is it Y3T? Y3T?
No. This is y2 of the. So this whole thing is
Yeah,
y3 of t. Right? So the take home message here is that if you know the individual inputs and their corresponding individual outputs, you can form new inputs by scaling each one by different amounts and adding them together and make a new waveform. And you don't have to send that waveform through this to find out what the output is going to be. You can predict that by linearly combining the individual outputs by different amounts and adding together mathematically, right? It's a way to mathematically model any output. So it turns out that the same trick works for time delay also. So let's say I have time invariance property. So let me erase this and then I'll write it afresh. So now what I'm going to do is I'm going to delay x1 by tau1. I'm going to take x1 t by tau1. It produces y1 by tau1. x2 t by tau2 produces y2 t by tau2. Individual delays on the individual signals produce the corresponding individual delays on the corresponding output paths, right? Now, I take the time version of this linear time invariant part, right? The time invariant component is corresponding to the time delays, tau1 and tau2. But earlier we looked at the amplitude variation in gain, alpha 1 and beta, right? So I can now write, okay, if my new input x3 of t is the scale version alpha x1 t minus tau1, right? Plus beta x2 t minus tau2 I can now directly write down, right, by inspection, what the output is going to have to be. What's the output? Y3 similarly scaled, so alpha y1 similarly delayed t minus tau 1 plus beta y2 t minus tau. So the point here is that every component, the output side is simply scaled by the scaling factor that's occurring on the input side. And in the output side, all the delays are exactly what happened in the input side. It just carries forward to the output side. All right, so we'll take it from there.